All right, welcome everyone. Today we're going to be learning linear algebra for machine learning, and specifically we're going to be going over chapter 1 from the comprehensive textbook Mathematics for Machine Learning by Dijzenroth, Faisal, and Ong. We're going to be going over chapter 2, linear algebra, and I thought who better to teach us a lot of these concepts than the inventor or the forefather of a lot of them, Carl Friedrich Gauss, 19th century German mathematician, widely regarded as one of the greatest of all time, known for a lot of contributions not just in linear algebra but also in number theory, in differential geometry. We're going to be going over things like Gaussian elimination, and I think that without further ado, let's go ahead and introduce Carl Friedrich Gauss. Dr. Gauss, it's an honor to have you here.
Thank you, Karim.
All right, we're going to start out with systems of linear equations. Dr. Gauss, please give us an example of a system of linear equations.
Certainly. Suppose that a company produces products using resources. To produce such a product, such resources are required. Our objective is to find an optimal production plan where we produce without resources left over. Something like this. For instance, product 1 contains 2 units of this resource and 0 units of this resource. For example, a table may contain 5 wood and 0 glass. So in an optimal plan, the amount of wood is equal to product 1's wood times the number of product 1's, plus product 2's wood times the number of product 2's, and so on for all products. We do this for all the resources. We can represent resources as B, units of resources as A, and units of products as X. This is a system of linear equations.
And sorry to interrupt, but I just have one contribution that might help the programmers among us. You can picture it a bit like this. Professor, please continue.
Some systems of linear equations have no solution. Some have only one. Others have infinitely many solutions. For real-valued systems of linear equations, these are the only possibilities. Either none, one, or infinite solutions. If we plot these on a graph, the solution is their intersection.
All right, thanks so much for the concise introduction, Professor. Before we continue with solving these systems of linear equations, let's quickly recap basic concepts like adding and multiplying matrices.
We sum a matrix just like this, and here I demonstrate multiplication. If we have, for instance, a 5 by 10 matrix, it can only be multiplied by a 10 by x matrix. That is, it must have 10 rows.
Thanks. Please tell us about properties that matrices have, like associativity.
Associativity states that A times B times C is equivalent to B times C times A. If we multiply a matrix A by an identity matrix, the result is A.
Right, so it's like the number 1, but except for matrices, like 23 times 1 is still 23.
You may think of it that way.
Right. Now, not every matrix has an inverse, and later Dr. Gauss is going to show us a method called Gaussian elimination, which we can use to get the inverse of a matrix. First, I want to go over some more concepts. Dr. Gauss, please go over the determinant and transpose of a matrix.
I shall demonstrate. Consider this matrix. Here, for example, a 2, 1 means row 2, column 1. If we rearrange the elements like this, observe what happens when we multiply these together. It is all zeros, except it has this expression on the diagonal.
Right, it's like an inverse matrix, but except for ones, it has this.
Yes, So we can say it is the identity matrix times this expression. This expression is called the determinant. We can write the inverse as such. As for the transpose, we write the columns of A as rows. The rows of A become columns as such. Symmetric matrices are those that do not change by transposing.
Right, now this is crucial for data science because a lot of times in data science, we need to multiply a matrix by itself. So if we have a 2 by 3 and we want to multiply it by a 2 by 3, then we can't do that because the dimensions don't match, as we've seen previously. But what we can do is we can get the transpose of the second matrix so that now it's 2 by 3 times a 3 by 2. And in Python, the API, like NumPy, makes it very easy for us. We just write .t to get the transpose. And there are some other properties regarding inverses and transposes that are in the book. But now let's go back to solving systems of linear equations. Dr. Gauss, I know that you helped develop a method called Gaussian elimination. So can you please walk us through that?
My method involves writing the coefficients as a matrix, like so, with the results on the right. We call this an augmented matrix. Our goal with my elimination is to rewrite this into a staircase-like form where the rows start with zeros until they go past the row above them. We do this using elementary transformations. We are permitted to exchange two rows, multiply one row with a constant, and add or subtract two rows. We can even add or subtract a row times a constant.
Okay, I think that we need an example of this.
Yes, we have this system of equations. We start by writing a matrix like this. It is called an augmented matrix. We then apply some transformations. Remember that these are the transformations that we are permitted to do. We do row 2 minus 4 times row 1. Then we do row 3 plus 2 times row 1. Finally, row 4 minus row 1. Then we do row 4 minus row 2 minus row 3. We multiply row 2 by minus 1, and we multiply row 3 by minus 1/3. Now we can put this back into typical equations. We then can use this to find a solution. We notice that these equations look like a staircase. Look at these columns here. They are causing the staircase pattern, whereas these are not. We take these staircase columns and write them as a sum, with each one being multiplied by a variable.
Okay, so we're multiplying the staircase columns, actually called pivot columns, by variables, and we need to find these variables, lambda 1, lambda 2, and 3. Now, I'm going to reveal the answers first, and then later we show how to calculate them. They are 2, minus 1, and 1. You can see here when we substitute these, so 2, minus 1, and 1, we get the solution 0, minus 2, 1, and a plus 1. So when we have lambda 1, lambda 2, and lambda 3, we put them in a matrix like this. Now, lambda 1, 2, and 3 are not the end solution. If you look at the original problem, the variables we need are x1 to 5, but we can get them using lambda 1, 2, and 3. You see, when we bring back our solution matrix, x1 is going to be whatever we multiplied column 1 by, which is lambda 1. x2 is going to be whatever we multiplied the second column by, which in this case, we didn't multiply by anything, so x2 will be 0. The third column was multiplied by lambda 2, so x3 is lambda 2. The fourth column was multiplied by lambda 3, so x4 is lambda 3. The fifth column was not multiplied by anything, so x5 is 0. So here's our solution, minus 2, 0, minus 1, 1, and 0. So that's the process, but now let's see how to get those lambdas that I simply gave last time. Dr. Gauss, please show us how to do that for this matrix here.
Yes, given these linear equations, we arrange them into a matrix. Now, we look at the columns. There are two types. There are columns that help create the staircase, such as these. They are called pivot columns. And then we have those that trail behind. These are called non-pivot columns. We need to express the pivot columns in terms of the non-pivot columns. We write this column as this one times 3. We write this column as 3 times this one, 9 times this one, and minus 4 times this one.
All right, now we're going to cover the -1 trick, which is an easy shortcut to get a solution. Dr. Gauss, please take us through this.
Certainly. We have our previous matrix. Now, we add -1 rows as such to create a perfect staircase. The solution is the columns that contain a -1.
Yeah, I mean, I love how simple that is. So that's Gaussian elimination, and one of the applications of this is in calculating the inverse matrix, which, as we said previously, is we multiply a matrix by its inverse to get the identity matrix. And so please walk us through the calculation of an inverse matrix.
We use the previous method, but using different matrices. As we seek the inverse of this matrix, we create a matrix with our given one on the left and the identity on the right. We then use elimination so that it is in our staircase pattern, also called row echelon form. The inverse matrix is the right one.
All right, so we can use Gaussian elimination to solve systems of linear equations and to get the inverse of a matrix.
Exactly.
All right, brilliant. Now, I do want to point out that the actual concept of inverse matrices was not introduced by Gauss, but actually by Arthur Cayley. But Gaussian elimination still remained the actual method by which we calculated an inverse matrix. Now I'm going to go over some other approaches that we can use because, Dr. Gauss, as I understand it, your method doesn't work on all matrices, right?
Yes, the matrix must be square and invertible.
Yes. And if a matrix doesn't satisfy the square and invertible properties, obviously we can't use Gauss elimination. And the other thing to point out is that we can use the Moore-Penrose pseudo-inverse in these situations. I'm looking here. It was described in 1920, 1951, and 1955. It only works if the columns are linearly independent. And I do also want to point out in the context of machine learning that Gaussian elimination is not actually used by computers because here we're dealing with systems of millions of variables and Gaussian elimination just doesn't scale up to that. I'm looking here, I have a list of other methods that can be used, like for example, the Richardson method, the Jacobi method, successive over-relaxation method, Krylov subspace methods. We're not going to be covering any of these in this episode, but Dr. Gauss, I wanted to say thank you so much for being here and demonstrating all of this to us.
Yes.
It's great to hear it from you.
So.
And I hope to have an extended conversation with you later on in the future. Thank you so much.
Thank you for having me.
Thank you.
Dankeschön.